welcome to the Manchester Java community. So this evening we've got a couple of talks. First one is going to be Swapnil. He's going to talk to us about JIT compilation with Graal. And then after that, if you choose to hang around, it'll be slightly less interesting, I imagine, but I'll be doing a talk on communities. So yeah, I think just to say thanks to our sponsors. So we're sponsored by RecWorks, who are a recruitment agency based in London, who also run the London Java community. So they cover all our Meetup fees. So huge thanks to them as ever. But other than that, I think, yeah, handing over to Swapnil to get into the talk.
Thanks, Nick. Thanks, everyone, for joining. So as Java developers, we know that Java programs get converted into Java bytecodes, and those bytecodes are executed by a JVM. We also know computers use machine instructions, assembly language to run. But when I was learning Java, I was quite curious, like, hey, how these bytecodes or our source program gets converted into the assembly instructions. So for example, if I write something with add, like adding 10, then I expect somewhere there would be an assembly instruction that does addition, and I couldn't see that. So if you are in the same situation as I was, this is the talk for you. So today, we will see if the clicker works. First, we'll look at the overall how Java program works, the life cycle of a Java program. And then we will take a simple program with a small method in it, and we'll see how it goes through different stages of execution. First, it gets executed by the interpreter. So we'll see what it is, how to see what interpreter executes, how fast it goes, how slow it goes, why is it so. Then we'll look at the compilation. So when a method gets called over and over again, it gets compiled. So we'll see that part, and we'll see the actual assembly for our method. We will also modify our example a bit later, and then we'll see how the optimization, a compiler optimization would optimize code, and we'll see the assembly for that as well. So here the idea is not to talk and teach about compilers, and it's quite a vast topic in itself, but the idea is to give you the tools so that if you want to poke around the code base and look at how a particular part of the compiler works, then you should have all the tools to go ahead from this talk. And the idea is, like, when I looked at the code base for OpenJDK, it was in C++, so that added another twist, which had a bit of learning curve, quite significant learning curve, to be fair. So I was quite put off by that I couldn't learn and get what I wanted to know. So hopefully this talk will give you the tools so that the same examples that you have in the talk, you can tweak them, change them a bit, and then try all the things that we have seen, like generating the assembly, seeing how a particular optimization works. And if you want something like, say, how Java avoids multiple null pointer checks in a program, how it reduces them. It doesn't do it every single time. So you can form your own use case, your own program, and see how that happens and where exactly that happens. And you can also see the code, and hopefully you will get enough knowledge to even change it and play around with it. So all these slides are available on GitHub. I'll also show this QR code and the link at the end of the talk. So let's get going. So in the slides, just a quick note about it. So there would be a gray box at the bottom. Wherever it's possible, it will contain the commands that are relevant for the current discussion on the slides. And the same commands, you don't need to write them down. They are also available in the scripts in the Docker image that I put in the GitHub. So let's get going. First thing first, let's say we have a Java program called mytest.java. We compile it using JavaC and then run it using Java space mytest. So far, so good. So it takes, we use the Java program through Java C, which is the ahead of time compiler, which converts Java source into the .class file. and that we give it to this java.exe or Java binary file, which we call a Java virtual machine, the VM, which also accepts some input and gives us the output. Cool. So let's look at this Java virtual machine a bit closely. So Java virtual machine, whenever you execute a program, and basically when you execute a program, you start executing the main method and some other method. So basically you're executing methods. So when your method is getting executed, first your JVM gives it to the interpreter. And your interpreter, the interpreter in the JVM would execute your method. And when the method is getting called over and over again, JVM says, okay, hold on, this seems to be an important method. So let me compile it for you. So what it does is it will take the method and submit a request to the compiler. So in JVM, there are JIT compilers, which will take this method compilation request. They will compile them in the background, and then they will give the generated assembly code or machine instructions to the JVM. So what JVM does, when it submits the request, it will wait for the compilation to happen. And in the meantime, if you call the same method again, it is again given to the interpreter. So the method gets interpreted until the compilation is finished. And when the compiled version of your method is available, then JVM says, okay, the next time when you call this method, I'm going to go ahead with this compiled version of the method, which is relatively faster. And this is the trade-off that Java, the virtual machine-based executions typically do compared to the ahead of compiled approach. So there are many different implementations of JVM available. For example, one is from Oracle called Hotspot, which we are going to use for today's talk. But there is also also an implementation available from Azure, Amazon, IBM, and many different providers. They have their JVM implementation available. So for the Hotspot JVM, we have two JIT compilers in it. So they are called JIT compilers because the compilation happens just in time during the execution of the program itself. When a particular method is hot, JVM says, okay, could you please compile this for me? And the compilation happens. So that's the reason they're called JIT compilers. So in Hotspot JVM, there are two compilers, client compiler and server compiler. So what happens is when a method is called over and over again, first it is given to the client compiler to compile. And if the same method still getting called again and again, then it is given to the server compiler. So what's the difference? So client compiler will try to give you compiled version of the code a bit faster than the server compiler. So it will not do certain optimizations. But if the method is still getting called, that means it is an important method. So then you give it to the server compiler. So you say basically take as long as you want, but give me the best possible version of this method that you can. So that's the main difference. And this is this way of going from the interpreted version, then to the client compiler, then to the server compiler is basically the tiered compilation that JVM uses. And other implementation, the mainline implementations that we have, they also go with a similar approach with one or more just-in-time compilers. Today, we are going to use Graal. So Graal VM for today's discussion is the Hotspot JVM using Graal as the top tier JIT compiler instead of the server compiler. So we'll see more about Graal later. Cool, so let's take a simple program. Are there any questions by any chance so far? Cool. So this is a simple program, our my test that we saw earlier. It has the method myIncrement. which basically takes integer argument A, adds 1 to it, and return the result, which is integer. And then we call, in the main method, we call this particular method with value 5. So we expect it to return value 6. Cool. So when we compile this class with Java-C, we get mytest.class file. We can extract the bytecodes generated for mytest file using java-p-c command. And you will find the bytecodes for this myIncrement method as well there. So you can see here, there are 4 bytecodes that are generated for myIncrement: I load 0, I const 1, I add, and I return. So these are the 4 bytecodes only that basically do addition of, they add 1 to the argument. Cool. So when we execute this method, let's say myInt, oh, it should be myInc5, then in the interpreter, it will start its execution from the first bytecode, I load 0. And here is the thing: the interpreter assumes JVM as the stack machine. So basically, all the bytecodes will specify the operations that are performed on the stack. So that stack where you push and pop the operands. So all the bytecodes, if you look at their definition and the meaning, it will be something to do, some operation to be performed on the stack. So here, when you say, when you execute I load 0, it will say load the first local variable. This is from the doc, but basically it says load the first argument that you have passed, which is value 5 on the stack. I const 1, which will load the constant value 1 on the stack. So we have 5, then 1. Then we do I add, which will pop the 2 operands, 5 and 1, add them, and put the result on the stack again. And all this, you may have figured it out by now. I is for integer, and there are also alternative different versions for the other data types. So we have 6 on top of the stack. Now, when we execute I return, as you would expect, it will pop the value from top of the stack and return it. And that is how the execution happens. Now, you may wonder, like, okay, this seems simple, but it is, I mentioned it is also slow. So how slow it is? So what I did, I took the same myIncrement method and put it in, put some benchmarking code around it. And the same code example is also available in the Docker image. So you can run this and execute it in different modes. So first, over here, in the first column, you have this different mode of execution. So first one is for executing purely in the interpreter mode. The second one is the tier 1 only, which is using only C1 compiler. And the third one is the Graal compiler. The score column is the score. So how long it took to execute the particular myIncrement method. And these are the units, so nanoseconds per operation. Here, one operation means one execution or one time executing the myIncrement method. So now you can see the interpreter takes way longer than the client compiler. And Graal will give you even faster version of the code, but you wouldn't see much difference here from client to Graal, because we have a simple code. As the code, your example gets more and more complex, you will see the power of using the aggressive JIT compiler. Cool. So you may wonder, okay, this is the interpreter is about 70, less than 70 times slower, but why is it so slow, right? So this is the assembly on the right. This is the sequence of assembly that would be executed when you call or when the interpreter executes I load 0. And remember here, what we are doing is in my increment, we are just adding 1 to the argument, right? So somehow we just need to load the value of the argument, add 1 to it and return the result. But then here we are having these many instructions just to do iload 0. And there are 4 such bytecodes. So, and here is the size of the instructions or the bytecode. So if you count the entire size, which is not a perfect measure of code quality, but you can say it's roughly indicates it roughly indicates the quality of the code that's been generated. So here interpreter executes about 1,200 bytes of code. C1 executes about 336 bytes of code, and Graal will give you the higher code quality by doing more and more optimizations. So different modes of execution basically trade off certain things. So on the left, when you have interpreter, you have the lowest time to start up. So you don't need to do any compilation. You can start the execution right away. And as you go towards the higher tiers of compilation, you spend more time in compilation. You do as many optimizations as you can, or the compiler can, and you try to improve the quality of the code. So naturally, it results into faster execution. And based on these trade-offs that each compiler makes, you need to decide whether to use only interpreter or the top tier JIT compiler. So you cannot use only interpreter because it will have faster startup time, but overall execution would be way slower. And if you use only the top tier JIT compiler, then it will take much longer to compile the code, and then you will have the actual working application. So what happens? Well, I said you need to do it. So what JVM does is, when you execute the method for the first time, it will go ahead with the interpreter mode, and it will say like, okay, if something is important, so how does it decide a method is important or not? So it decides based on how many times it is called. And then as you call it more and more number of times, it will recompile the method with the next tier of compilation. It is also like, it's not visible here, but if you are thinking, if your method is called more than 2,000 times, but over a longer period of time, so there is whether it will still be compiled with the Graal or top tier JIT compiler. So what happens is each compilation request is also having some time associated with it. So that is how compiler would decide whether this request is still valid or not. So if it takes much longer to compile something, so compiler may say like, oh, probably this request is too old. There is no point in compiling it, and it will ignore it altogether. But you can find all this information. You can extract it from the JVM. So because we are talking about the code quality, our my increment, if we write it in C, you will just get what you would expect, the add instruction and return instruction, right? And this is the ARC64 assembly, the ARM assembly on the right. So you will see this W0 is the result value. W0 is again the first argument, and this 1 is the constant one. So you add 1 to the argument and put the result in W0, which is also the register that is used to return the result. And it will become more relevant as we go further. So we looked at JIT compilation, and when compiler decides that a method should be JIT compiled or not. So, okay, so you can use this raise of hand option on your screen. So how many of you think if we execute our mytest.java, how many compilations would happen? How many of you think there will be 0 JIT compilations? can use raise of hand or use the chat option. 1 for my increment. Yes, no. One, okay. And how many of things more than 10, there will be JIT compilations. Cool. So we can extract information about all the compilations. And you can see if you execute your myTest class, you will have many of these methods getting JIT compiled because, and interestingly, none of these methods would be your my increment method or any version of that, because what happens is your my increment is getting called only once, and we saw until it's called 2000 times, it wouldn't be JIT compiled. But before your code gets executed, there are many other components of the JVM, many subsystems such as class loader. It will be called to load your class and execute it. So it would do some class name parsing, so string parsing. So you will see quite a few methods from java.lang.string, then java.lang.math, and so many of them. We are not going to look at them, but when you will see the output, you will also see the compilation request ID here and the tier with which it got compiled. So you have this java.lang.object, its initialization, which is getting compiled with the top tier JIT compiler, because you may have initialized many objects until you execute the actual myTest class. My increment method. So it will give you some interesting information as well. So because now we are talking about the compilation, get into the compilation. We are going to use Graal VM. So you may have come across Graal VM before. So you may have heard it in the context of running different languages, running ahead of time compiled binary, or many other uses of Graal. But for today's discussion, Graal VM for us is just the hotspot JVM, which has Graal as a top tier JIT compiler. Okay, so interesting thing about Graal is Graal is written in Java itself. So the whole idea behind this talk is to give you out to show you that you can use all the tools that you use in your day in, day out Java programming, you can use to learn Graal itself. So when I was learning, when I tried to learn about how the compilation happens, it was in C++, which I couldn't learn all the things that I wanted, but it wouldn't happen with Graal, because you can also, you can use whatever editors, debuggers, tools that you have with the Graal itself. And basically Graal is a simple program which takes bytes, array of bytes, because bytecodes is array of bytes. It processes them and generates the assembly. Again, assembly is a sequence of instruction, ones and zeros. They are also bytes. So it takes an array of bytes and generates an array of bytes. And while doing this, it will use some intermediate graph representation and many other, I think it's pretty common for the compilers to convert the programs into the graph-based representation because it is optimization friendly. So all the optimizations that you will find in Graal, there will be some sort of operations being done on the graph and nodes of the graph. And it will make more sense as we go further. So if it is a Java program, we would expect it to be something like this, right? We will have some array of bytes as input. We will have this Graal class. Then it will have some sort of compile method so that JVM can call this compile method, give the array of bytecodes for a particular method. And then this compile method will return array of bytes, which is assembly instructions, right? And these assembly instructions then JVM will use whenever you call the method again, it will use this compiled version. So we expect Graal to be something like this. And let's see whether we can find it. So this is a screenshot, and because it is a Java program, we can put a breakpoint and we can debug it. So this is the screenshot when I was debugging the compilation of our my increment method. So here you can see certain variables. So we have this, the current object, which is of type hotspot Graal compiler. So instead of Graal class, we have hotspot Graal compiler. Okay. We also have some variable called graph, and we have result, which is of type compilation result. So we will look at each of them closely. So here we have this compile method as we expected. It returns the compilation result, which we will see in a moment. And it takes the arguments. The first argument is structured graph. So it's the graph object. The second one is the method. So it's resolve Java method. And you can see here, I used IntelliJ. So it also showed the values of those particular variables. So this is hotspot method. And this is our myTest class. And myIncrement method, which this is the signature. It has integer type argument. Cool. So let's see how this method looks like. So this is the same method with myTest, myIncrement. I open the at the panel that where you can expand the variable and see their values. And in method, we have this code variable, which is a byte array. And if you remember, we are trying to find whether it takes byte array as input and generates the byte array as output, because it is a Java program. And we are looking at the compile method, which takes the argument. One of the arguments is method, which is our myTest.myIncrement method. And it takes the byte array, which contains the bytecodes that we saw earlier. So we saw earlier myIncrement method had 4 bytecodes, and here we have 4 values. If you are still not convinced, I took screenshots from the Wikipedia. So these are the bytecodes. I load 0, and 1 is its value in hex. So if you can do the hex to decimal conversion in your head, you can see these values are matching. And of course, this is the signed byte. So it's the negative sign is coming from the value greater than 128. But this is, I hope I convinced you that this is the byte codes that are being given as input to our compile method. And these are the byte codes exactly for our myTest dot myIncrement method. So this is again the name of the method. Now, to check whether we get the byte array as output, we are looking at this result variable, which is of compilation result type. And it has a field called target code. And again, this is a byte array of size 232, and these are the bytes. And these are basically ones and zeros. These are the machine instructions that will be produced by Graal, and they will be used when our myIncrement method is called. And this will be the compiled version of the method. This is the code size, and you can see other variables as well. This will give you some interesting information. So we saw we got input as byte array, we got output as byte array, and in the middle, Graal converted our code into this graph-based representation. So you will see a graph variable, which is of type structured graph. And this is the graph for myTest.myIncrement, which has 6 nodes. And these nodes are, you can see the node IDs are 0, 1, 3, 4, 5, start node, parameter 0, constant 1, then there is this addition node, and then there is return value. So to visualize this tree or graph-based representation, there is a tool called Ideal Graph Visualizer, IGV in short. So you can download this tool and visualize the graph-based representation. It would look something like this. So here you have your start node, and the return node, and one is in orange, another one is yellow and red, or yellow and orange, and they're connected using this red orangish line. So this is the control flow line, and the blue one is the data flow line. So when the execution of this method starts, it will begin at the start node, and it will return the value, which is computed by computing addition of this value P0 and constant 1. So it will add P0, which is the parameter 0 or our argument A, and it will add 1 to 8, and whatever the result will be the return value or the result of this particular method. And these 1, 3, 4, these are the numbers or IDs of the node. And that is how you read the graph, and you will see more interesting information from this IGV. Okay, so now we want to see how this graph-based representation will emit or generate the assembly instructions. So each node will have this generate method. So add node in this case, because we saw add node here, 4 is plus, which is of type add node here. So you can go to add node.java and you can look at the generate method, and it will tell you what this node will generate, what assembly instructions or a sequence of instructions it will generate. So here you can see on line 202, it has gen.emit add, and it is emitting the add instruction. Now, if you, because it is the same ID, you can step down or try to see which classes have implemented this particular method. So if you do command click or control click, you will see the implementations. And here you will see this emit add method is implemented by 2 different classes. One is for ARC64 and one is for AMD64. So ARC64 arithmetic LIR generator and AMD64 arithmetic LIR generator. So here you can see until this point, this graph-based representation was completely platform agnostic. All the optimizations that you would do, they would be same for both Intel and ARM hardware. But from this point onwards, Graal is checking, okay, now I want to generate the assembly instruction. So which type of hardware I want to generate the instructions. So here we are going to step into this ARC64 arithmetic LIR generator to see what assembly instruction it would generate. And now you can see the add that we were looking for since the beginning, because we are adding 1 to a variable. So this is the add instruction. And if you slightly look around in this method, you will have different variations of this add instructions. So these are the instruction that ARC64 or ARM instructions that's supposed to do floating point addition and addition with setting some flags, but you can dig into it a bit more. So you can use your editor to find more information about it. And when you look at the assembly, you can extract the assembly code for, that Graal had generated, or any tier of compilation had generated. So here you can see this W0, this add instruction, W0, W1, and this hash constant 1, which basically says W0 equal to W1 plus 1. By the way, if you remember, we had this C output where we had W0, W0, and 1. And here it is W0, W1, and 1. So we are using the second argument from that is passed to this function, which is in W1. Does anybody like to guess what will be the first argument to a Java method, the default argument? It's this pointer, this. So it's always, this is the first argument, and the second one is the one that you actually see in the method. So that's the implicit one, this pointer. So Here you can see your add instruction that we were basically looking for since the beginning for our add method. And the code around it is setting up the stack. If you look closely, if you're interested, you will find some more information about it. There is also some interesting discussion about this poll return. If you're interested, you can find me later. So why this instruction is there. But in general, this is our myIncrement method and its assembly. So let's make our example a bit more complicated. So here we have our same myIncrement method called from the main method. And before adding 1 to it, we are calling myMultiplication, which basically does a multiplied by 16. So we are multiplying the argument by 16 and then adding 1. So if you pass 1, it will multiply by 16 and add 1. So it will return 17. And we are calling the same method 1 million times because we want the method to be JIT compiled. By the way, we looked at the invocation thresholds, and they were like 2,000, 15,000 kind of thresholds. By the way, you can also change them by using JVM flags. But then here we are calling it million times. So the reason is that, we have audio disabled. So the reason is that when the method gets, when JVM says like, okay, this method seems to be hard, let me JIT compile it, it will submit a request for compilation, but it is not ready yet. So it will wait for the compilation to happen. And in the meantime, if you invoke the method, it will go ahead and call the interpreted version of the method. So we are calling it million times so that it will be still executing the myIncrement method, and the compilation will finish in the background. It will be available, the compiled version will be available, and we will call the compiled version. So that's the whole rationale. And all these codes and these flags are also available in the Docker image. So if we can generate, we can ask Graal to dump all the information that it generates during the compilation. So you need to use certain flags. They're also added over here, these dump flags, and that will allow you to see all the stages that your code has gone or your method has gone through. So this is for each method, you get all the information, what optimization Graal has done. So here, when our bytecodes for our new complex method got parsed, the graph-based representation looked like this on the right. And here you can see the same start and return node. It is returning the addition with 1, and the value 1 is added to the result of multiplication, and the multiplication is with arg-a, first argument, and 16. So if you go back, it's the argument multiplied by 16, the same a, and we are adding 1 to it. So that's what we are seeing here. And if you notice, while generating this graph-based representation, we had 2 methods, myIncrement and myMult, and Graal has inlined both of them. So we see code or graph for both addition and multiplication here. So multiplication was part of myMult, which you can see as part of myIncrement. So this is the inlining optimization. So this is when the bytecodes are passed by Graal. So at the end of all the optimizations, you will see, so here, if you click on this, you will see how the graph looked like after all the optimizations. And you can see the multiplication node, this node number 5, got replaced with node number 10, which is the left shift. And multiply by 16 is equal to left shift by 4 for integers. So you can see the compiler has optimized our multiplication, and this optimization is called strength reduction that you may have already learned. So here the idea is multiplication takes longer. So historically it took a longer time than the shift operation. So we want to simplify the computation. So instead of doing the multiplication, we are doing the left shift, which is considered as faster. You may be surprised, some hardware may compute both multiplication and left shift in relatively same time, or you wouldn't notice any performance difference even if you replace it. So this is the left shift. So multiply by 16 is replaced with left shift. The same optimization goes for the division. So instead of left shift, you do the right shift. And you can go through all these different optimizations and see how the graph looked like. So here you can see we have this high tier after high tier, after mid tier, after low tier. So all these performance agnostic optimizations that Graal does, and before generating the code, they are divided into so platform agnostic optimizations. They're divided into 3 categories: high tier, mid tier, and low tier. And you can see which actual optimizations that are performed in high tier. So IGV will allow you to dig into that information. So you can extract all the information about not only how the graph looked like after a bunch of optimizations, you can also see how it looked before the optimizations and after the optimization. So high tier will have all these optimizations, mid tier and low tier. It will perform different optimizations. You can see some familiar names such as inlining, loop unrolling, loop peeling, and some optimizations may be done multiple times. So phase canonicalizer, so optimization pass is referred to as phase in Graal. So you will have class names that are called canonicalizer phase.java or optimizediv.java. And you see canonicalizer is getting called twice. So this canonicalizer optimization tries to simplify the node, so complex operations into simple operations. Some dead code elimination, again canonicalizer. So this is the sequence of optimizations that Graal will perform on each method. And now it may give you some indication like, hey, why the top tier JIT compiler takes much longer time to give the compiled version of code, because it does all these optimizations on each of your method. So we were looking for the optimization that changed this multiplication into the left shift. So many optimizations follow the visitor pattern. So you will, when you are exploring the code base, you will see it quite used a lot there. And there are 2 interesting methods here: canonicalize and generate. It's canonical. So these 2 methods are of our interest at the moment. We want to see what happened, what changed our multiplication node to the left shift node. So if we open the mulnode.java and look at this canonical method, we will see it takes 4 arguments. The first one is stamp, which carries the type information. So it is the integer operation. So it will be stored there. Then this for x is the x argument of x operand. Long I is the constant, the second operand, which is 16 multiplied by 16 we are looking at. We don't want this node view at the moment. So here we are checking in canonical method. If the value of I is 0, that means we are multiplying a number by value 0. So any integer multiplied by 0 is 0. So we are returning constant node of value 0. If we are multiplying a variable with value 1, it's the same value that we want to return. And you can see how these three nodes with operand, the for x value, the long I value, and the multiplication will be replaced by constant 0 if we multiply by 0, or only the for x value or the argument a when we multiply by 1. When we multiply by -1, instead of doing the multiplication, it will replace the whole multiplication by a negate node, which will say like, okay, negate the for x value. And here, when value of I is greater than 0, which is of our interest, our value of I for us is 16. So it is greater than 0. It is a power of 2. So then we are replacing it with left shift node. So here we are replacing multiplication with left shift node, and left shift is performed on for x, and we are computing the value to be left shift if we multiply by 16, which is 4. Left shift by 4 is multiply by 16. So here you will see how the multiplication is simplified into the left shift operation. Oops. And when you will see the assembly, you will have this OR instruction, which is basically doing OR of the 0 register with 1, which is W0 equal to 1. And then we are having our add instruction, W0 plus W1, which is our argument A left shift by 4 plus 1. So this is our result. And this is what we were doing in our my increment. We were multiplying by 16 first and then adding 1. So this is has happened in only one instruction, add instruction. By the way, you may wonder, you said like we had this multiply node, and then there was this left shift node that we switched to, and then add node was independent, right? So we should have seen some left shift instruction and then add instruction. So we have one instruction that does both addition as well as left shift. So where did this optimization happen? So there is another part in Graal, and many compilers do this as well. So they use match rules. So in the graph, you will find a particular pattern, and you will see like, hey, for this particular platform, so here we are looking at ARC64 node match rules. So for this platform, I have an instruction which can do both add and left shift together. So here on line 316, you have this match rule. It uses some domain specific language similar to Lisp. Add is performed on, add is the operator performed on X, and another value, which is the left shift of Y and a constant. So this is the pattern it's trying to match. So there should be a left shift, which comes before the add, and the value of left shift, the result of left shift is used in add, and then you can perform both of them together. And the left shift has also a constant here. So you can see emit extended add subshift. So this is basically saying like, okay, instead of emitting 2 instructions, just emit 1 instruction. Now basically, instead of this multiply and add node, emit this, use this particular node which emits only 1 instruction instead of 2. And you can see more such rules in ARC64 node match rules, and there is also AMD64 for Intel or AMD hardware instruction set. So in summary, we looked at Graal as a JIT compiler. So how Graal takes your method, the my increment method, and converts from source program to assembly. Then we looked at the graph representation, how to read it, and the graph, how Graal optimizes the graph representation. And we looked at some of the platform-specific optimizations, such as the one using the match rules. So instead of emitting left shift and add separately, we emitted only one instruction, and some platform agnostic one where we replace the multiplication with left shift, and how Graal generates the assembly instruction. So the idea here is all these examples that we have seen, they're very simple because we will understand how the code base looks like, where to look for, what is the overall flow that a method goes through. But then all the complex scenarios as well, you can form your own synthetic test case to check how the lock elision happens, or how the null check is eliminated, how a particular dead code is eliminated. You can go through, you can change the same code that is present in the Docker image. You can just create your own example, and you can see the generated assembly. You can see the optimization has happened, and then you can dump the information and look through the ideal graph visualizer so that you can see like, okay, this particular optimization has changed or has detected this particular pattern. It has removed this null pointer check, for example, or it did some constant folding. And then you can look into the source code and see like, okay, this optimization is actually doing a particular task. So how it does it? And then that is how you can go with particular understanding particular optimization. We haven't talked about many things, which is instruction scheduling, how the graph representation is transformed into the sequence of instructions, register allocation, Graal intrinsics, where you basically have a method and you tell Graal like, okay, don't touch it. I know the best sequence for this particular method, and it wouldn't touch it through all the optimizations. And at the end, it will emit a sequence of instructions for that particular method. So this is how roughly the intrinsics work. The native Graal's native image, or Graal for running other languages, and other JVM components such as class loader, garbage collector. These are significant parts of the JVM itself. So we haven't looked at it. We only focused on the compiler, but I hope this intro or overview will help you to poke around the Graal code base and get some interesting insights for your Java application. Thank you. Questions? These are the resources that I use, and the link if you want to use.
Yeah, that was brilliant. Thank you, Swapnil. That was a real deep dive. I'm not sure how often I have to think at that level of systems. But yeah, if anyone's got any questions, please drop them into the chat. Yeah, here's a question to start with. First of all, amazing talk, thanks. So this is from C. Morales. Do you have any recommended resources to dig into the topic?
Yes, so basically, you can start with the Docker image that I've uploaded on the URL. And these are definitely the resources. You will find these links as well. So this is how you can play around with it. But in the Docker image, you can take the same examples and do, let's say, you change the method to have another pattern. So some sort of constant folding, or the, let me see, I haven't added the blog reference. So Mechanical Sympathy is a blog where you will find really deep dives, or Alexei Shiplev's blog, you will find really deep dive into a particular topic. So Alexei Shiplev will do more GC focused blogs, they're quite intensive. And on mechanical sympathy, you will have relatively small sized blocks, which I found very useful as well. So there you can take the same examples from there, put it into this benchmarking setup, and then generate the assembly. Look how Graal works on it. Those ones are for C2 and hotspot, but you can try the same for Graal.
Great. There is another question from Michael Kepler. So how do they avoid optimizations running endless circles, transforming back and forth, e.g. fold versus unfold or similar?
Oh, yes. So that's basically heuristics, and you manually check that. And you also write some tests to ensure that it doesn't go in endless loop. So for example, there is an optimization of reassociation. So if you add, let's say, 3 plus a plus 2. So what you do is you reassociate 3 plus a to a plus 3, so that you can do the constant addition of 3 and 2 there. So you can say a plus 5 or something like that. So it may happen that the reassociation will keep happening all the time. If in one optimization, it will reassociate and the other one will change it back. So that happened once, but then you basically make sure like you manually ensure it doesn't happen. There might be other ways of doing it programmatically, but I've seen the manual approach and some heuristics to say like, okay, even if you compile and compiled version assumes certain behavior, so you de-optimize if something else happens. So if it keeps de-optimizing, it will get more and more generic, but at one point it will even stop doing optimizations to say, okay, let's go with the interpreter mode.
Right, cool. So another question here for you. So this is, I suppose I'm kind of thinking about ARM's implementation. So how mature is Graal's ARM implementation versus Intel at the moment, would you say? And as a kind of a follow-up question to that, are there any major optimization advantages on ARM that you found?
Right. So, I mean, it's difficult to claim credit of certain behavior or something that is done purely by the hardware and saying like Graal or we or somebody else implemented it nicely. So I would say Graal's implementation, yes, it's catching up with x86 or Intel's implementation. Majority of the benchmarks that we see, we have the comparable performance. The primary work that at ARM we took was the intrinsics to provide intrinsics for strings, for example, and some of the other Java methods. So it's catching up. I mean, it's kind of more than 90% complete. And the other methods that are not supported as of now, they are not used often. So that's just from the feature completeness side. Some of the benchmarks may show you much higher performance on a particular hardware. I'm not sure I should take the names, but some hardwares are really fast. So they are like their cache hierarchy and everything is like the other hardware aspects come into play to make it faster. So then the other competitive hardware. So that would not be just Graal, but it would be like, okay, this hardware is fast itself.
Right. Cool. All right. Well, yeah, I think we've got some great questions. Another question. So we'll ask this before we finish up. So given that we now have a compiler implemented in Java purely, is it foreseeable that the old compiler written in C will vanish at some point?
Well, we have to speculate. So it would be, well, Cliff Click, one of the writers, early writers and famous developer of JVM, he said that if I have to write compiler again, he would, or the JVM, he would use Java instead of C++. So Java is mature enough. when would that happen, or if that would happen, is a different story. Because if you look at the ahead of time compilation state as of now, it's not as fast as what you would get with like the top or the mainline GCC or Clang or other ahead of time compilers. So changing the C++, the entire implementation to Java is a really big undertaking. So not sure just changing the entire implementation for will give, if it does not give any additional performance benefits, would it make sense? Because it's been developed a lot longer. Yeah, from I think 93, 94.
Yeah, I suppose it's a lot to think about in kind of being able to meet those same goals effectively.
There are research JVMs written. I'm not sure whether the entire JVM is written in Java, but Maxine VM and JIT VM probably they have big. So Graal originally was part of Maxine VM. So I'm not sure whether the entire Maxine VM is written in Java, but larger than the regular JVM is written in Java for Maxine.
Oh, that's interesting. Okay, cool.